4. Welcome everybody to day 1. We're going to be comparing assertions to actions. And what does that mean? It's a paradigm shift. I love this Escher picture. You have pictures. You can think about the green pictures or about the black pictures. And it's always useful to have more than one way of looking at things. People tend to think about algorithms as a sequence of actions where you go this direction and that direction, but the problem is you might get lost. So we're going to think instead about landmarks. What is a landmark? In our context, it's an assertion. And what is an assertion? An assertion is a static picture of what is true at this moment in your journey, at this moment in your computation. So my landmarks, I was born in Washington, went to Waterloo, went to a graduate school, undergrad in Waterloo, graduate school at U of T, postdoc at Berkeley, and then I'm at York. All right, so these are where we're starting new slides. Suppose my boss wants me to write some code. What does he give me or she give me? She gives me the precondition, what's true about any assumption about what must be true about the input. Before you can write the code, you need to know what kind of inputs are going to be given. And you need to know the postcondition, which is any statement that must be true about the algorithm and the computation once it returns. And what's the contract? The contract is if the precondition is true about the input and you execute the code, then when you get to the bottom, the postcondition needs to be true. All right. And what do you give your boss back? You give her code. All right. So now we're going to do a little 1090 math because people aren't as good at logic as they should be. What does A imply B mean? All right, so let's look at just some examples here, right? Suppose the precondition is true. What does that mean? If the client gives an input that meets the precondition, right, then what should happen? Well, your program better meet the postcondition, right? So here's preconditions true, postcondition true. And is alpha imply beta true? Have you met the contract? Yes, you've met the contract. Everybody is happy, right? So here's another situation. Suppose you go out into the world and the client gives you an input that does not meet the precondition, right? And oops, here I got my circles in the wrong place. I wanted a circle down here. Suppose your program does not meet the postcondition, right? Is that a problem? Have you broken the contract? The answer is
yes.
No, you haven't.
No.
No, they might not be pleased, but they can't be mad at you because the contract was only that you get the postcondition met if the precondition is true. So for example, if the inputs are supposed to be numbers and the boss and the client gives you a bunch of elephants, then you can't expect it to work. All right, so the code still meets the contract. All right, so when can people be upset? When is the contract failed? It fails when the precondition is met, but the postcondition is not met, right? That's when everybody's going to be upset at you, right? Everybody follow that? All right, let's go on to a sub piece of code. All right, the question is, how can we prove that this sub block of code works, right? It's hard enough to prove an entire program works. So we're going to narrow it down to proving a block of code works. And And of course, we have to know what the definition of work is, right? So we're going to put in these assertions, an assertion before the code and an assertion after the code. And what is an assertion? It's any statement that must be true when you're at that spot in the code. Feel free to ask questions, though I think it's pretty straightforward compared to what we've done in the past. All right, so what is our statement here? Our statement is, suppose the computation gets to this line right here at the beginning of the code and it meets its assertion. Then after executing this code, when you get down to the end of the block, it should meet the assertion at the end of the block, right? Does that make sense? That's what working means, right? Now, we can then ask, well, what happens if the computation is at the top here and it doesn't meet the assertion at the beginning of the block? Well, then what do we do? Well, before we were saying it didn't matter what your code does, but now we're going to say if you get here and this assertion's wrong, then you should panic and display some sort of box that's saying there's an error message, talk to your administrator. All right. So what's our definition of correctness is that if the assertion at the top of the block is true and you execute the block, then when you get to the bottom of the block, the assertion at the bottom of the block needs to be true, right? So that brings us to an implication here. And implications are surprisingly confusing. In 1090, I spent quite a bit of time on them. So let's remember whether you took math from me or you took 1090 from somebody like George, I'm sure you all did deduction, right? So what's the usual form of deduction is you say, I want to prove that some left-hand side gives me some right-hand side, implies some right-hand side. So what you do is you assume the left-hand side, then you do a bunch of proving, and somehow you prove the right-hand side. And your conclusion, your deduction conclusion, is that the left-hand side gives you the right-hand side. The reason we indent here is because while we're indenting, we're under the assumption that the left-hand side is true. We don't know for sure it's true. We're just under that assumption. So let's talk about that. Here I say we're assuming the left-hand side. How do we know that the left-hand side is true? And I've given you a hint already. We don't know for sure that it's true. But there are two cases, right? It's either it's true or it's not true, right? So let's think about the two cases. The one case is that the left-hand side is false. And what's true when the left-hand side is false? Is that we don't care, right? We don't care what's happening. It could be, it doesn't matter. So if we're in the logic world, what we would say is that left side implies right side is automatically true when the left side is false. But let's not get into that scary whole dialogue that we spent a long time with. Let's just say when the left-hand side is false, when the assertion is false, remember, we don't care what the code does. We're going to put up an error message or something bad has happened, and we just don't care. But what we do care about is if we get up to the top of the loop and the assertion at the left-hand side here is true, then we better prove the right-hand side, right? Does that make sense? And so then we still beg the question, how can we assume that the left-hand side is true? Well, the way we can assume it's true is because that's the case we were considering, right? If we were considering the case in which left-hand side was false, then remember that was the I don't care case. We're in the left-hand side is true case, and that's what we mean by we're assuming that it's true, right? Everybody follow that? All right, so now, you know, I have lots of characters. You can see a bunch of characters on the screen. In 1090, I assumed that I had an oracle. You know, you climb up to the top of the mountain and there's a burning bush that is able to tell you wise things. And in this case, she was telling us that the left-hand side was true. She was assuring us all the implications of the left-hand side. All right. Now in 3101, sometimes I'm going to talk about the fairy godmother. I'm at the top of the loop. I can ask for whatever I want to be true. I'm going to ask the fairy godmother to assure me that the assertion that I'm currently on is true, right? Another way I talk about it is let's say we fly in for Mars and land right here on this line. Our Martian here will assure us that this assertion is true, i.e. that this left-hand side is true. All right. All right. So now we're down here. The Martian is assuring us that we're at the top of the loop and the assertion is true. And then we need to execute the code. And it's complicated. Even this teeny little weeny little example, it's complicated what the code does. And the reason it's complicated is that there are two paths through the code. And so that is kind of like having two cases. So let's talk about proof by cases. I don't know whether you did that with George, but certainly when I was proving logic, I came up with this whole idea of proof by cases. And how do we do it? We say, let's say there's some gamma that we want to prove. We're going to prove it by cases. Then what do? The first thing we have to do is somehow identify what the cases are, right? And I'm going to say there are two cases. Either alpha is true or beta is true. And the reason the or there is because, well, they're not both true, but one is true or the other. We only have two cases in this situation, right? So we prove that either alpha is true or beta is true. And then what do we do for the first? We say now we're doing the first case. In the first case, you assume alpha is true. Why? Because that's the assumption, that's the case you're doing. And then knowing alpha is true, you go ahead and prove gamma. And then you say case two. In case two, you assume beta is true because that's the case. And you go ahead and prove gamma. And now what do we know? What can we conclude? Well, either alpha is true or beta is true. And either way, we get gamma. So we say proof by cases, we can conclude that gamma is true. Is everybody following this? Holler if you don't.
Yes.
Excellent. So now let's relate this to what we're saying. We're trying to prove something by cases. And what we're trying to prove by cases is that the assertion will be true when we get to the bottom of the block, right? That's our goal, is to prove assertion one. So how do we do it? Well, we're going to have two cases. I told you that there were two paths. So you check the code and you verify that there are only two paths, and you call the one path alpha, you call the other path beta, and you say, those are our cases. Then you consider path alpha. You say, we are following path alpha. That's an assumption. Do we know we're following path alpha? No, but that's our assumption because that's the case we're doing. And given that assumption, we have to prove that when we get to the bottom, that we have assertion one is true, right? And then we consider case two, that we're following the beta path. And then given that we're following the beta path, we have to prove that assertion one is true. And then we can conclude that either we followed the beta alpha or the beta, and hence the assertion's true, right? Does that make sense? Those are our steps. All right, so to do it, I don't want to just say the value of x, because the value of x changes. And whenever the value of x is the same within some sort of block, then I won't talk about this value versus this value. But if the value of a variable is going to change, I better give me some notation. So here the notation is let x sub 0 be the value of x when we're asserting assertion 0 at the beginning of the block. And let x sub 1 be the value when we get to the bottom of the block. All right. And now let's look at the case 1 game. All right. This is what you have to prove in order to prove case 1. So let's go through it. Why are we assuming that x0 is an integer? Why? Because I'm saying we're flying in from Mars. We're landing here at the top of the block. The block, so we're assuring that the Martian is assuring us that assertion 0 is true. And assertion 0 is telling us something about the value that's at the top of the block, which is x0, and it's telling us that x0 is an integer, right? That's what we know from the Martian. All right, now how do we know this? Well, remember we're doing case alpha. That's telling us we're following this block. We're executing the first, first part of the if statement. And given that, we know that the if condition must be true if we're doing the first path, right? And what is the condition? The condition says that x is odd. We still have the same x0 value, so we're saying x0 is odd. That's our condition. So what about this down here? This is a funny thing. We're assuming that we're executing this first pass. So we're executing this first block. And what is this block? This is code. Code takes the old value of x, adds 1 to it, and gets us the new value of x. So I'm translating that code into a math statement, because over here we're doing math, and the math statement, right? This is x equals x plus 1 is not a math statement. Can't be true. But here's a math statement which tells us the relationship between the old values of x and the new values of x. All right. And then let's bring us over to here. What we're trying to prove, our goal is that when we get to the bottom of the block, that assertion 1 is true. And assertion 1 says that x is even. And of course, at that point, we have the value x1 is the value at the bottom of the block. So our statement is that x1 is even. All right, does that make sense? And what do we have to do? Yeah.
Oh, sorry. So saying like x initial is an integer is like the first assertion, and then the x initial is odd is the second assertion under the first assertion?
Iterations? No, we don't have a loop here. There's only one iteration.
Oh, no, I meant, because like, you know how you were showing the indent?
Yeah.
Like there's an assertion and then an indent?
Oh, yeah. Oh, no, no, this is all, no. This is all case. The case is that we follow, right? So this is what, we're at the top of the loop. The fairy godmother or the Martian is assuring us that this assertion is true. Now we're going to have two cases. The one case is we follow alpha. The other case is we follow beta, right? So we're currently doing the alpha case, right? And in the alpha case, we know from the Martian that that's true. We know from the case, from the fact that we're following alpha, we know that the condition has to be true, right? And from the case, the fact that we're following alpha tells us that we execute x equals x plus 1, which gives us that relationship, right? So the green is coming from the fact that we're sure that this is true, right? And the orange and the blue are coming from the fact that we're executing this code, right? And then the green down here is what we need to prove, right? Does that make sense? Right? And so we need to prove this. We have to prove if all this on the left is true, right? We assume everything on the left is true, and then we have to prove the thing on the right. And so somehow you have to argue that if you assume the left-hand side, you get the right-hand side. And if what you're proving here, what you need to do, let me tell you on a test what you need to do. You need to write here enough to convince the TA that you know what's going on, right? And I'm not going to write anything right here. I'm going to just say, hey, if X is an integer and X is odd, and I add 1 to it, then it's going to become even, right? That's the level of math we're going to be doing here, right? So I'll tell you, again, let me tell you that all this setup here, the setup is I'm going to be anal about. You have to get it perfect to get marks. But this proof part here, if to get an A+, you have to give a good argument, and to get a B, to pass the course, you can just wave your hands around a bit. All right. We're a little less concerned about that than I'm concerned about the whole setup. Does that make sense?
Yeah.
Right.
I just have a quick question.
Yes.
Like, you know how in here we only have like conditions, we don't have any loop. So basically, but then the topic is like loop invariance. So do we
It's not yet.
worry about any invariance in like just the conditions?
So people, I used the first time through, I went into loop invariance and people got confused. So I'm asserting here, this is not about loop invariance yet. Yes, I know that's the topic of the section, but right now we're talking about assertions versus actions, and the green are our assertions and the blue are our actions. And we'll do loop invariance in 5 minutes. Okay.
Okay. Because I was just asking like if we have any invariance, and yeah.
5 minutes from now, we'll do loop invariance.
Okay.
Right now, we're doing case B, case beta. The fact now we either followed alpha. How do we know we followed alpha? We don't know we followed alpha. We know we either followed alpha or we followed beta. So there's 2 different cases. And in this, and we did the alpha case, so now we're going to do the beta case. And so we're going to assume that we follow beta. Why? Because that's the case we're considering. All right. So what are all our assumptions? The one assumption, we collect here all our assumptions. One assumption is that we got to the top of the block and assertion 0 is true. Right? Why do we know that? Well, because otherwise we don't care what happens, right? We know that because we were assured by the Martian, right? What about this? Well, we know that we're following case beta, and case beta says that we do the second half of the if, which means that the condition fails. And if the condition fails, then it's not the case that x0 is odd. And then we execute this code at the bottom, right? And so the code says don't do anything, all right? But should we put nothing here? No, we need to put something here. We need to know, in order to get what we want, we need to know the relationship between the old values of x and the new values of x. And do nothing is translated into the fact they're the same, right? Everybody good with that? Then what is our goal? Under those assumptions, we need to prove that when we get to the bottom, that the assertion is true, right? So again, how do we prove that? Well, we're going to assume by way of assumption that everything on the left is true. And then we're going to prove that then the right is true, right? And again, it's pretty straightforward that if x is an integer and x is not odd, and you don't change x, well, if x is not odd, then it's even, because if it's not odd and it's an integer, this is where we're using the fact that it's an integer. If it's not odd and it's an integer, then it better be even, right? So, and we don't change it. Everybody get that? All right. So here's another example. somebody was keen on doing loop invariants, but we're going to do a scarier example first. This is just a sequence of ifs and elses, right? So what's our definition of correctness? Is if you fly in for Mars and the top assertion is true, and you do some code, crazy, you do this code somehow, when you get to the bottom of the code, you need to prove that the assertion at the bottom is true, right? That's definition of correctness. And why is this hard? Is because you have to check every possible path that goes through this code. We're going to have to do it proof by cases. If this was the computation, if this was the computation, if this was the computation, right? So how many computational paths are there? Well, there's 2 choices for the first if, 2 choices for the second, 2 choices for the third. How many such paths are there? There are 2 to the R paths through this code. Everybody follow that? So if we were going to do proof by cases, it's not the running time of the code that we're concerned about. It's the running time of my proof. My proof will have 2 to the R cases, and I don't want to do that. So is there a faster way? And yes, we're going to first step 1 is going to say, we're going to insert more assertions. And step 1, which we're going to say, if assertion 0 is true, assertion 1 is true. How do we do that? Now there's only 2 paths, right? We get our first path, we get our second path, and we conclude, the red line is what we're concluding. We're concluding is that if the assertion 0 is true and you execute this code, then assertion 1 will be true, right? We're proving that the first if works. And then we do the second if and the third if. When we get down to the last if, again, there are 2 cases. We do the 2 cases, the first path, the second path in those 2 cases. And again, that we can conclude that if assertion R minus 1 is true, then when we get to assertion R, it will be true, right? Does that make sense? But now what do? Now we have sequential code. What do we do with sequential code? Well, there are all these blocks. We broke our code into a sequence of blocks. And for each block, we prove that if the beginning of the block is true, then the end of the block is true, right? But the end of one block is the beginning of the next block. So how do we combine all of these things? What is it called to combine these? Think 1090.
Induction?
Nope.
Chain?
Nope. All right, so say A0 gives me A1, A1 gives me A2, A2 gives me A3.
Transitivity.
Transitivity. Transitivity. Everybody got that? Very well, whoever said transitivity. All right, so the joy is instead of having 2 to the R paths, we only have R subpaths, right? We solved each of these R subpaths, 2 to the R, they're 2 to the R subpaths. We solved them, we proved for each of them that it worked, and we could combine it that the whole thing worked, right? Does that make sense?
Yes.
All right,
Can
so
I
now here's just a simple example, right? I start off by saying the precondition that I have 3 numbers. I set M to be A, and then I assert that M is the maximum number in this set, right? So here I prove that if this is true and I do this code, then that is true, right? And then I prove that if M is the maximum of A, and I compare M to B, and maybe I improve it, if B is bigger, I shift it over B, that proves me with 2 cases, right? It said if M is the maximum of A, and then after you do this code, 2 cases, I get that M will be the maximum of A or B, right? Does that make sense? And see here I have my 2 cases. Condition 1 is that B is bigger than M. Condition 2 is that B is not bigger than M. Either way, I get that M is the maximum of A and B, right? And then I do the next one and the next one. And at the end, we know that M is the maximum of A, B, or C. So all I do is I return M, and then I get the post condition that the output is the maximum of A, B, and C. Right? Everybody follow that example?
So the assertion 2 is for the post condition. Assertion 1 is for the precondition.
I think this is assertion 0, assertion 1, assertion 2. This is the post condition. This is saying if we have assertion 0 is true and we execute this code, then we get the post condition.
I just have a quick question about the previous slide.
Yeah. The transitivity?
Yeah. So you know how in transitivity is like if A equals to B and B equals to C, then A equals to C.
Yeah.
But then how do we connect the assertion 1 with assertion R minus 1?
Oh, sorry. I was thinking that maybe that was confusing. Let me, that's in real time. Sometimes. All right, so let's bring this down here and say assertion 1, assertion 2, right? So here 0 gives you 1, 1 gives you 2, and hence 0 gives you 2, right?
Mhm.
And then we know that 2 gives us 3. So that gives us that 0 gives us 3. Does that help?
Sort of. Because I'm also thinking, you know how assertion 0, when assertion 0 is true, assertion 1 is true, when 1 is true, then 2 is true, right? And then so on. So but
Yeah.
then how do we connect the one, like the one that is true with the starting of the another one, which is like assertion R minus
That's
1?
why I added this one in here. See, the end of one, assertion 1 is both the end of the previous block and the start of the next block,
Mm-hmm.
right? So when we first prove the first block is true, we prove that if assertion 0 is true, then assertion 1 is true. And when we prove that the second block is true, we prove that if assertion 1 is true, then assertion's true is true. And then we use transitivity to combine those two blocks into one block to show that if assertion 0 is true, assertion 2 is true.
Oh, okay. So what happens in the middle doesn't really matter, basically.
Well, yeah, so that's where, yeah. So what we want to know is that if the beginning, if assertion is 0 is true, then assertion R is true, right?
Mhm.
That's what we want to prove. And how do we prove it? Well, we prove that if 0 is true, then 1 is true. And we prove that if 1 is true, 2 is true. And then we combine them by transitivity to say if 0 is true, then 2 is true.
Okay, that makes sense now. Thank you so much.
Yeah, yeah, excellent.
Professor, is there a case where say like say if we have like 100 assertions, right, and in the middle somewhere one of the assertions is not true? Like right
Then-
now we're saying that it is true. That's why we're saying
Yeah.
transitivity can work.
Yeah, yeah. So remember what happens. What happens when an assertion turns out to be false? What do we do?
Then the loop invariant will also be false. But
Yeah,
it-
the whole program crashes and burns.
Yeah.
You're gonna so what in the end, what do we want to be true in the end? Right. In fact, here, let's go to this example here. Now, what we need in the end to prove is I didn't write it here. I should have written it here. In the end, what we want to prove is this. Right. gives us right? So this is our final goal, right? If the precondition is true and you execute the code, then we need the postcondition to be true, right? Now, assertion 2, way in the middle somewhere, will it be true? Well, if the precondition is not true, then all bets are off about anything, right? At any point, it could fail, right? It might not fail right away. Maybe precondition is true, code will work for a while, and then it will hit assertion 2, and that's where it will crash, right? And a box will come up and say there's a problem, all right? But we're kind of going under our whole assumption. We're saying if the precondition is true, then 0 is true, and if 0 is true, 1's true, and if 1's true, 2's true, right? And blah 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 blah. And if assertion's true, then the postcondition is true, right? And if you combine them all into transitivity, what you get is that if the precondition is true, on precondition being true, right? If the precondition is true, then I want all your assertions to be true. If the precondition is not true, then I don't care what it does, right? I don't care when it crashes and burns, right? Does that make sense?
Yeah, that does. Yep.
All right. So we're ready to do another piece of code, which now has a loop in it, which is good because you know the topic of this section of code of slides is called loop invariance. All right. So what's our definition of correctness? It's the same as before. If the precondition is true and you execute this code somehow and you get to the bottom, then the postcondition will be true, right? That's what our goal is. So we can ask the question we asked before. How many paths are through it? For each path through it, we have to check that this thing is going to be true, right? We have to say proof by cases. If the precondition is true and we have this path, then we get the postcondition. If the precondition is true, we have that path, then we get the postcondition, right? There's all these different paths, right? So the question then is, how many paths are there? Anybody know? You saw it, it was on the slide a second ago. We could go straight through, skipping the loop. We could loop once, twice, 3 times, 4 times, 5 times. There are an infinite number of paths, right? Because for any, even if we're saying conditioned on the fact that we exit, we could loop 5 billion trillion times, right? So there are a lot of paths. So do we want to check them all separately? No, same as we did before, that would be too much work. So what we're going to do is we're going to break the computation into subpaths. And those subpaths are going to be, what's a subpath? It's going to take you from one assertion. We're going to add one assertion in here. One assertion, we could add assertions wherever we wanted. The classic place to add it is at the top of the loop. And so now, then once we have these assertions, we're going to have a subpath just get us from one assertion to the next assertion. All right. So what are our subpaths? We have to get from the precondition to the loop. We have to get to the loop, back to the loop. And we have to do that back to loop, back to the loop, back to the loop, back to the loop. That's all the same. And then we have to get from the loop to the post condition, right? That gives us 3 subpaths. Does that make sense?
So does that mean we're like kind of treating like as one assertion, even though it's a loop where we have like technically the assertions like looping again and again, but we treat it as one because of the
This
transitive?
is an assertion. It states that when you're here, this needs to be true. And when you leave that, right? So that means when you get to it, it needs to be true. If you leave and you get back to it, it still needs to be true. If you leave it and you get to the post condition, it still needs to be true. Anytime you get to the top of the loop, it needs to be true.
So can the loop invariant in this slide, it's below the start of the loop, so we can have it below, or does it have to be before? Because then if it's below the loop, would that be an assertion? And then if it's if it's below the loop, meaning like inside the loop, it'll be an assertion. And then if it's outside at the top,
yeah, if it doesn't loop, then it's called an assertion. Loops invariants are examples of assertions. Loop invariants are assertions that appear inside of a loop.
So then in this case, would it be like more correct to call that an assertion instead of a loop invariant? How like you wrote it?
No, because it's inside of the loop. It's the top of the loop.
Isn't that both the same thing? Like a loop invariant is an assertion?
Yeah. Okay. So my loop is this, and I stuck the loop invariant very carefully at the top of the loop. Now you might say about this exit, but the reason I have the exit after here is because I want to say I want the path from the loop invariant. I have 2 paths. I could either not exit, do this code and come back to the loop invariant, or I could be at the loop invariant. I could hit the exit condition, exit, and come down to the post condition, right? So I very carefully put the loop invariant at the top of the loop, and I put the exit condition after the loop invariant, because from the loop invariant, my paths branch. Right? You can think about this exit as an if statement, right? We're at the top of the if statement. We have this. We have an if statement that says, if the exit condition is not true, then do this code. And if the exit condition is true, then skip that code and come down and do this code. Right? Does that make sense?
So, Professor, do we have 3 paths then in this example?
Yes.
Okay.
There's the path from here to here, the path from here to here, the path from here to here. 3 paths. And we're going to have to prove that each of those paths maintains the fact that your assertions are true. Right?
So I'm still confused about one thing. For like, okay, so like the loop invariant is there just because it has to be true for you to enter the loop, right? So then why is it inside the loop?
Because it always needs to be true when you're at the top of the loop.
Okay,
what is this location? This is the location at the top of the loop.
Okay. All right. Okay.
Right. And the first thing you have to say, from the precondition plus this code, I have to get my loop invariant. How do I establish my loop invariant? How do I maintain the loop invariant? How do I get the post condition from my loop invariant? Those are our 3 steps. Right? Does that make sense?
Yeah.
The way I see it is that the loop invariant doesn't stop you from doing anything or let you do anything. It has nothing to do with control flow. It's more like for validity at a certain point.
Exactly.
Like assertions aren't like if else statements. It's not like if the assertion is false, then we might do something else. It's like at this point, we want to make sure that something is true. We're not actually checking it with code, but that's the way I see it.
Exactly.
Yeah. What I was thinking about it was like if like technically it being like an if statement that isn't actually code being before the start of the loop, but I guess you could have it.
It's not an if statement. Well, it's sort of an if statement. You can think of it as if this is true, go ahead with your life. And if it's false, then bring up an error, throw an error message.
Like a try catch or something almost. Just
I'm a little confused because, like, I don't know if it's okay for me to discuss this right now, but like, there was the monster problem.
Yeah, that's way ahead.
Okay, well, I'll bring that up later.
You can bring it up when we fit it. Right now, we're recording this bit of slides to put into the guys, so they don't want to hear about the monster problem. Any other questions about this code? Oh, here, I added some extra thoughts here. What are assertions for? They're useful for thinking about algorithms. They're useful for developing algorithms, describing algorithms, proving correctness of algorithms. What is an assertion? It's a picture, it's a statement about the current state of the data structure. It's either true or false, right? Example, your bank account is not negative, right? Assertion is not a task, right? It's only a comment that's added for the benefit of the reader and for the benefit of the person writing the code. It helps you write correct code. And it's there to make sure nobody gets lost, right? As long as the input meets the precondition, somebody some man asked me the other day, last class, how is the assertion independent of the path followed and of the input? And I was a little shaken by that, I will confess. And I added this little caveat at the beginning, right? If the input doesn't meet the precondition, then all bets are lost. But as long as the input meets the precondition, then the assertion should always be true, no matter what path you follow, no matter what the input is, right? Does that make sense? I didn't have that line before and that confused people, right? If it's false, then something's gone wrong, right? What is an assertion formally? It's a function takes as input the current state and it returns true, false. So what is the current state? Well, it tells you everything that's true at a particular instance point in the computation, right? Imagine you flying from Mars. What do I need to tell you everything about your computer so that you can continue the computation, right? It doesn't say anything about the past computation. It doesn't say anything about how I got there. It just says what's true right now. So if you remember, if you ever took 2001 from me, I had states of my Turing machine, which might tell you the values of various variables. It tells you what line of code I'm on, right? It tells you useful things, right? That's the state that I'm in. And so what is an assertion? Here, an example of an assertion is that X is odd. So what does that mean? That means if I'm in this state, then A is a function from the state I'm in to a true or false. Well, in this state, X is odd, so it's true. And in this case, X is even, so it's false, right? And in the first example, the computation is on the path. It's on the path towards glory, towards everything being okay, right? And if the loop invariance, if the invariant assertion is false, then something went wrong, right? Does that make sense? The last statement in this section will be, don't be frightened. Assertion doesn't need to be a lot of formal math, but you can put formal math in there if it helps you. You can use a picture or a description, right? It's in English, right? Does that make sense?
We need to measure progress. I don't know why that was sticking in there. This is just saying we need to prove that we terminate, right? Oh, here we're going back to our measure of progress. All right, what's a measure of progress? It's a function that takes as input the current state, and what does it output? It outputs a real number, right? So here, my measure of progress might be the value y, and so here, if that's my state, then the measure of progress is 3, right? And you need to prove that every iteration that number goes up or down. Yeah? When do we do it? You can do them in different orders. I would say generally for a test, you don't do it until you've got everything else done. And then if you still have time, you can fill it in. And if I really want you to do it, I will tell you to do it. But usually it's so obvious that the program halts that we don't bother. The only time we do it is when it's not clear whether it'll stop. Or more precisely, we do it when, actually no, I lied to you completely. I lied to you completely. Let's start all over. I'm going to give you a whole different answer. All right? You ready for a different answer? There's going to be a separate question on the test which asks for the running time, right? And the running time doesn't just tell you that it will stop. It tells you how long it's going to take to stop, right? So it's an extra addition. And how do you do running time is you say, well, I have to make this much progress, and how much progress do I make per iteration?